In this one page of notes, I will be calculating the concentrations of all reactants and products at equilibrium once it's been established from an initial set of concentrations given at the start. This is part of Unit 7 in AP Chemistry called Equilibrium, and it's Topic 7, Calculating the Equilibrium Concentrations, but it could be part of your college level course when you cover the topic of equilibrium. What's commonly used is something called a Rice table, where you have the reaction, initial, change, the equilibrium concentrations, but with an X value given, like algebra, and then the final equilibrium concentrations, which is our end result. We're going to take this reaction with its initial set of concentrations and equilibrium constant and find these equilibrium concentrations. All right, so let's get started with the reaction itself. So carbon monoxide gas is going to be CO gas, and it's going to be reacted with water vapor, so that means it's gaseous water. And at some point it will reach equilibrium, these gases, to create carbon dioxide gas as a product, and then hydrogen gas as the other product. This is balanced with all ones in front of each reactant or product particle. And then the K value, the equilibrium constant value, which I do talk about in a separate video before this one, is going to be around 100. We'll just round it to 100 to make the math easier. And that's at a specific temperature because the K value will not stay 100 at a different temperature for this reaction. All right, the other thing is we have an initial concentration, just to make this problem a little bit unique. We have an initial concentration of all of our gases, and I won't be using pressures, we'll use concentrations. And so let's say they're all 0.1 molar at the start of this reaction. What I'm going to do first, though, is write what's called the equilibrium expression, which is the K value. And then you're going to have the products concentration, so this is a Kc. And you might even see like at 500 Kelvin. You could put to the 1, but most people do not, and then the hydrogen. And in a separate video, I go over how you write equilibrium expressions. And then carbon monoxide and water. And again, you know, typically we would not be putting those 1 values up there. They're kind of understood. All right, and then that's going to equal 100. So that's the set K value that will happen no matter what these initial concentrations are. This equilibrium will get established with the products being favored and 100 meaning that it's product favored by 100 times. So I'm going to put over here that this is a product favored equilibrium. So product favored equilibrium. And that's because the K value is greater than 1. And I talk about that in a separate video that you may want to watch as you go through these sections. All right, the first thing we're going to want to do is calculate a Q, which is a reaction quotient, and I did cover that in a separate video also. So let's calculate what the Q is, and I wanted to have some really easy numbers for this to go faster. So all of them are 0.1, so that makes this a little easier, but I'm still going to show the work. So a Q just means that they're an initial set of concentrations. So I'm just going to put that in green here. So this is our equilibrium. Basically, these are the concentrations at equilibrium. And I'll just switch to a different color. And then these are just the initial concentrations. And we don't know if we're at equilibrium. And in fact, we know we're not because this is just going to equal 1. And so what we'll say then is something that I talked about again in a previous video is that Q, let's put it over here. Let's just sneak it even smaller here. Q is less than K. And what that means is we have to shift what's called shift right to make more products. So we're going to shift right. We have to make more products because the denominator is almost like too big and the numerator is not big enough. Okay, so then let's figure out then that means the shift is this minus X. And then that means you're going to lose some of our reactant and gain some of our product. And I kept this pretty simple so that we don't have any moles. These are all 1 to 1 if you wanted to put that in there. So these are all 1x's versus like a minus 2x or a plus 2x. So then you're just going to say 0.10 minus x, and we're on to, like I always call it now, we're on to the algebra land. And then plus x, and then 0.10 plus x. The K value is not negligible, so what we can't do is anything where we ignore that X, which I talked about in a previous video. We have to actually keep the X values in there. Now, our final answers are going to go here. And I'm going to come back to this part of the chart, the rice chart or the rice table, but that'll be at the end. So now we just have to solve the mathematical part of this, which is that the K value is going to be equal 100. And the set of conditions that we had is 0.10 minus, or sorry, plus x, and 0.10 plus x. That's in the numerator. And the denominator is the minus x1. So be careful, these look really similar. And then really what this is, if you want to combine them, is it's 0.10 plus x squared, and then 0.10 minus x n squared. So this is going to be where they call it a perfect square. So we can take what's called the square root of both sides, and we can simplify the math by doing that. So we're going to take the square root of 100, and then we're going to take the square root of the value that I just had over there. I'm just going to zoom in. So 0.10 plus x squared, and then 0.10 minus x, and then squared. So we're going to end up kind of simplifying this to basically, I'm just going to move over 1. 10 is going to equal 0.10 plus x, just to keep this to one page of notes. That's kind of my purpose with these in each section. And then now we just proceed with, I would call it the algebra. I will actually work through all of it just in case this is maybe your first practice problem. So we're going to take 10, and then we're going to multiply it by 0.10 minus x, and then leave the 0.10 plus x on this side. And then just like you've learned in math class, we're going to combine all the like terms. So then we're going to have, I'm just going to push this through though. So we're going to have 1, because 10 times 0.1 is 1. Or you can do 1.0 if you'd like. And then minus 10x. That equals 0.10 plus x. And then now I'm going to push the terms so that they have the same ones on each side. So I'm going to keep this one over here, and then I'm going to subtract the 0.1. And then I'm going to keep the x on this side and add 10. Kind of a use for algebra, which is kind of cool. And then 0.9 here, and that's going to equal 11x. And then just like you've learned, you just divide both sides by that. And when everything's kind of said and done here, I'm just going to put over here, x is going to equal 0.082 m. So when you do that math, that's what you get. So then that's our x value, but now we need to put it back in to solve for all the concentrations. So kind of above, the carbon monoxide and the water are going to be the same, and I'll solve that kind of at the same time. And then our carbon dioxide is going to equal the hydrogen. And to do that, I'm just going to put the value in there. So I'm actually going to switch to green just so you can kind of see the difference here. So 0.10 minus 0.082. And then we get a value of 0.018. And then the other one is 0.1, and then plus that x value, which is small. Okay. But it does create more product. And then 0.182. And then I'll put those numbers back up at the top where they belong, kind of up here. So 0.018 molar, 0.018 molar, and then 0.182 molar, and 0.182 molar. So I have officially solved the equilibrium concentrations. And then what I'm going to do is just double check within a little bit of error. Those 4 concentrations should give us the K value of being 100. So I'm just going to do a little check here at the bottom. Is that, do I get approximately 100 if I put in those values? I'll even put them in green. So if I take 0.182 and then just twice, so square it, and then 0.018 times 0.018 or square it. And if you check, you do get pretty much approximately within significant figures. And you could even turn it into scientific notation like that. We do pretty much get the Kc again at 500, because if we change temperature, then the K value would change.